Okay, so just continuing with our previous concept video on using Jacobians to analyze the velocity of a mechanism. Here we're going to be using the Jacobians to analyze its acceleration. So this is all the information from the previous concept video. We've got a drawing of the mechanism, the vector diagram that we used, and all the information derived from the first Jacobians, as well as the Jacobian for the system, and the equation we use to get the velocities, as well as our Q set. Anyway, from this we can also use the identity that gives us our acceleration, which is simply going to be thus. So to get this equation here, well, first of all we can get this term rather rapidly by just changing around this one here. So all the q dot, we just change it to a q double dot set, or a double derivative set. So just to save on paperwork, and we'll get something like that. And for the second term of this equation, we're going to be taking the derivatives of each term in them, the partial derivatives, and summing up. So for this part here first, before we multiply it by our q dot, taking this part here, and for the first term of our Jacobian, cos theta 1 is going to remain constant. So for both of these terms here, those will be 0. For our second term in the matrix, we'll be dealing with cos theta 3, and the only term changing is our cos theta 3, our theta 3. So taking the derivative of that will give us negatives cancelling out from the differentiation to give us theta 3 dot sine theta 3. And for our third term, we've got two terms in our Q set that are changing. So first of all, we'll consider first of all, we'll do the differential with respect to theta 3. Give us theta 3, like so. And next we'll do it with respect to R3. So the differential of R3, sine theta 3. And again, we can do the same for the bottom row, which will give us minus this time. And doing this one here. So first with respect to theta 3, then with, not with respect to, but in terms of theta 3, and then for our R3. Right. Yeah. Anyway. So now we can multiply, or rather, forgot about the minus there. So now we'll take the minus into there, and we can multiply it by our q dot set. Yeah, q dot set. So to find this side of the equation, well, obviously our zeros from the dot product, we're not going to get any terms from our R1. From our R3, we're going to be multiplying it, or rather R3 dot, we're going to be multiplying it here. R3 dot, theta 3 dot, sine theta 3, and taking that minus into it here. We're also going to be having this one here multiplied by our theta 3 dot, and again taking the minus in, and this term here. So it'll be our total top term. Now the bottom term, taking the minus in, they cancel out. So we get a positive R3 theta 3 cos theta 3. And again, making sure we count the minus. We'll get our minus theta 3 dot and this term here. So now we have one side of the equation here, given here, and we have another side up here. So we can equate these two to each other, and there'll be two 2x1 matrices, so we'll get essentially two simultaneous equations in matrix form. So transitioning to a new piece of paper here, writing out the whole thing, our first term, this being our Jacobian multiplied by our Q double derivative set, and I've just gone and taken a simplification step here, same thing we did before, because our cos theta 1 is going to be equal to 1 and our sin theta 1 is going to be equal to 0. So straight to the second term here, factorable to 0. R3. And we'll set that one equal to our other matrix. Like this. And yep, this one will be R3 dot, theta 3 dot, sin theta 3, and just expanding the brackets from the previous one, we'll get this term here, and this term here. Just straighten that up. Yep. And similarly for the lower term. Cool. So this will be our full equation here, and because, again, same thing, this is going to be 0, we can get rid of both of these two terms here, multiplying by 0. So our unknowns in this situation, we derived all of these from our previous velocity analysis. What we don't have is these three accelerations here. So again, rather than using simultaneous equations or some kind of matrix form, we can just do each one separately. So the bottom line first, rearranging it to put it in terms of our R3 acceleration. So essentially our right hand term plus, set it there, yep. Oh, just one dot there. And dividing that by sin theta 3. Yeah, I mean this is our bottom line. Yeah, right. Now, substituting in those values, we got all these previously. So -6 for this one. Cos 30, subtract 1 squared, times our R3 value, times sin 30. And dividing all that by our minus sin theta 3, or sin 30. And we'll get an acceleration across length 3 of 24.248 meters per second squared, positive. And now we can put this into our top term. I'll put it over on the far left. So again, rearranging it in terms of R1 here. will give us, again, sorry, 1 dot. A lot of writing in Jacobians, like so. And now putting in the values, so -1 times our -6 for our free velocity, times sine of our angle, -1 squared, times our r free, times cos of our angle, subtract our -6, is 1 times sine of our angle, and now plussing our acceleration across length 3, 24.248 times our cosine of our angle, which is going to give us 24 meters per second squared in the positive direction for our R1. And so, put the dots there. So again, because our R1 acceleration is going to be considering essentially the acceleration this time, the acceleration of the ground with reference to our moving slider. Acceleration of the moving slider with respect to the ground is going to be acceleration of b. It's going to be -24 meters per second squared. And you can see that this makes sense as well. Essentially, if you draw it at, say, 2 different positions where the angles here are going to be the same, and it's moving in this direction. So as our slider moves along here, we defined, where is it? Yep, we defined our velocity of the slider itself to be positive, and R1 will be decreasing and thus negative. But as it moves further, the distance travelled over the same amount of time is going to grow smaller and smaller, so our acceleration is going to be acting in the negative direction on the slider itself, whereas the acceleration of R1 is going to be acting in the positive direction. So this gives us our velocities and our accelerations of all the lengths that we require. And that concludes the section on Jacobians.